So now let's see how we can use a frequency comb to make our spectroscopy better and faster. Okay, and to kind of grow in complexity, we start with one frequency comb for now. All right, so very quick reminder, frequency combs, we have this spectrum, which consists of equidistant T's, which in time domain form very, very short pulses, right? So immediately you can see it is like a CW, but we have all the CWs at the same time. So we no longer need to scan anything, right? So we come with this frequency comb, we have all the discrete lines separated by precisely the correct distance. So we kind of can kill two birds with one stone. We have a broad spectrum and we have coherence. We don't need to move anything like an attunable laser. So wouldn't that be good? Well, that's what people actually thought. And they came up with this scheme of how things can be arranged for spectroscopy applications. Well, you always have a source in your spectroscopy experiment, and this source can be one of these, many options, and Bill introduced us several options. So it could be a mod-lock laser, it could be a micro-resonator, it can be electro-optic comb. It depends on you really, and the choice is yours, because we need to know what spectral features we are measuring, how broad they are, and that gives us an idea of what frequency comb to choose, what separation between the lines we need, and also what we have in the lab. We not necessarily have all three in the lab, so it might be just one of them, right? So then we need to think about our sample and what we are measuring, right? What substance, what molecules, what absorption lines we are measuring. So majority of the experiments use one of these three options. We have either a single pass cell, so it could be a gas cell filled with gas, let's say. And it's good if the gas is very high concentration. It helps us because it gives us very strong absorption. Well, it might be not very interesting, because if you have a very strong, high concentration of gas, practically it may not be the scenario that you want to target. So you would need to deal with low concentration gas here, and then you have to have a very high sensitivity detection system. It might not be possible, right? So usually for realistic applications such as breath analysis and things like that, people are interested in billions per part detection. So this is extremely high sensitivity detection. You need to detect very small amount of molecules in your gas cell. So having a single pass might not be very practical. So in that case, what people came up with are these two options. Either a multi-pass cell, which in fact is not a cavity. So multi-pass cell allows your beam to go in and then bounce around, because these walls here are mirrors. But the trick is not to repeat the same path, so not to create a cavity mode, right? So it's pretty much the same scenario as here. It's just the optical path is increased by many, many, many trips. And then at some point there is a window, the beam is coming out and it's entering some sort of detection system. So that works as well. Designing those cells is tricky, but it's possible, and you can buy them from the optical companies. So another good option is optical cavity. And Martin introduced optical cavities very well, and there was Carla here, and the spring, right, all the modes. So in optical cavity, what you have is you have many, many bounces. The beam travels exactly the same path, which leads to enhancement of light. So what it does, it improves interaction of light with matter and enhances the absorption in that way. So the only thing you need to worry with this geometry is we have frequency comb as an input, and we also have cavity modes. So one needs to think how all these T's and modes overlap and what is going to be as a result of it, right? So you might be filtering some of your frequency comb tees with a cavity, and we'll see how it works in the demonstration later. So this is a very radical geometry where you can just take your laser and you just shine it in open space, and you hope that it will reach your detector. And sometimes people do it, perhaps not in highly populated cities or in forests because it's impractical, but you know, it's definitely been done, and that's for communication. There are scenarios where that's exactly what people do. All right, so now with regards to readout, remember that we still have a single frequency comb, so we have all this spectrum of these T's, right? So we need to use something for detection of these T's, and that needs to be a fairly sensitive detection because the T's are very, very narrow. So what people do is grating spectrometers, and VIPA stands for Virtual Image Phase Array. It's kind of a Bripiroid alone, so similar to a grating. That doesn't have much resolution, so it's about 0.5 gigahertz resolution. Might be not enough for you, depending on what frequency comb you're using, right? If you're using a micro comb with 20, 30, 50 gigahertz repetition rate, that's okay. If you're using a mod-lock laser type comb, that's not good because you have megahertz frequency. This thing is not going to resolve it, right? So you might need something which is called Fourier transform interferometer, and that's a Michelson interferometer with a moving, one of the arms is moving. So that's a wonderful instrument, gives you high spectral resolution, but it has a moving part in it, right? So it would resolve your spectrum, but it will be fairly slow measurement. So just to demonstrate things a little bit, we look at how some people did spectroscopy of molecular spectroscopy using optical cavity and Fourier transform interferometer. So I've just used it for demonstration, this publication. So that's fairly recent, 2019. And the work is about resolving rotational vibrational states of fullerene. Fullerene is a ball-like molecule consisting of 60 carbon atoms. So if you have so many atoms, then you have a lot of different motions. You have a lot of rotations and vibrations in your molecule. If your molecule is at room temperature, then you have a full forest of rotational vibrational states. It takes a little bit more energy to vibrate for the molecule. Rotations happen very, very easily. So you have, like, you cannot resolve anything at all. So to do this spectroscopy, the authors put fullerene into a gas cell inside this cavity, optical cavity, and they cooled it down. And that was to reduce rotational and vibrational oscillations. And in the end, what it looks like, they used a mid-infrared frequency comb laser. They pass it through this optical cavity. So what we can see here is a forest of comb teeth, which are filtered by the cavity modes, right? Every fourth comb tooth comes through the cavity, and they're able to obtain this wonderful result in the end, where blue lines correspond to the measured spectra, and black is simulation of what is expected for fullerene molecule. And we see it's quite well corresponding to each other, and everything is very nice and stable as well. So it just gives you an idea, but to do so, they use this FTI instrument, which is Fourier transform infrared spectrometer. I personally used FTI instrument. It's not very fast, so it might take about 10 seconds or so to generate one sweep in frequency, and you might need 20, 40 sweeps to get your signal-to-noise ratio right. So this is definitely okay for spectroscopy. It's best if you're not opening the door of your laboratory, not changing humidity in your lab or temperature, because everything moves because the calibration for the instrument move. So you can see that for a university lab, it might be a suitable option. But if you want to take this kind of thing into the field, it might be a little bit impractical. And by the way, FTIR spectrometers are quite large as well and not very cheap. Anyway, so what we are going to go into next is this thing here, dual comb spectroscopy, which helps to tackle the speed problem. And that actually is allowing us to read spectroscopic data without having a conventional spectrometer, diffraction grating based or FTIR instrument. Okay, dual comb. Good. So to start with dual comb spectroscopy, I want to go back a few steps and remind us all about heterodyne detection. So I think heterodyne detection is one of the best things ever discovered because it's so simple and it's so powerful, and Scott referred to it yesterday as well. So very quickly, optical light and optical range has very high frequency oscillation, right? 6 to the 10 to the power 14 hertz. So if we put a detector here, no matter how fast is the detector, we'll see DC current, right? So this is an average power. So to be able to measure frequencies, we need to somehow down convert the frequency to something reasonable, to a RF frequency range. And that's where the heterodyne detection is superb, really, and unbeatable. Because if you all of a sudden take a second optical wave, which is slightly detuned by a few kilohertz, for example, and you put it into your system and you're trying to detect it using exactly the same detector here, then instead of having a very high optical frequency, which you still have there, and it's still a DC current, you will have a bit node at the difference frequency, and this different frequency will fall into a range of your electronics, and you can measure it. So now what you can do is you can modulate one of these beams, right? You can, for example, change amplitude or phase of your second laser, and that will change amplitude or phase of your RF bit node that you can measure using oscilloscope or using an RF detector. So super easy and super powerful. So frequency comb using dual comb scheme is exactly like this. So first we take a one frequency comb with a spacing between the lines of FR, and we beat it with a second frequency comb, which is slightly detuned. By detuned, I mean that the frequency spacing between the bit nodes is a little bit different. And it's good if we can change by how much. So it becomes very powerful, actually. So what happens is, at some point, those two frequency combs will have completely overlapping T's. But then later on, they start to disperse a little, right? So to drift apart. And for every single next line, we have slightly more and more and more drift happening. So when we create a beat signal between these two, we pretty much create a difference, which is 0 here, and then it would be delta FR, which is our initial detuning, and then 2 delta FR, and so on and so forth. And if we choose our delta FR to be, let's say, 1 kilohertz, then all of a sudden we convert everything into kilohertz spectrum, right? So then we have two schemes to work with. And one scheme is called asymmetric, where our main frequency comb goes through a sample, and then it beats with a reference comb, which is slightly detuned in terms of the frequency spacing. And in that key scheme, we can measure amplitude of our absorption lines, and we can also measure phase of our absorption lines, which is actually really, really nice. Or we can just beat everything together, pass it through the sample, which is called symmetric or collinear scheme, and put it onto a photodiode, measure the spectrum, and what we'll see is intensity, drop in intensity where the absorption happens, and that would be only the intensity or amplitude measurement, right? So it's depending on what you're interested in. So by the way, this is a really, really good paper and explains physics very well. So, and I used it a lot for preparation of this tutorial. So now, if we look at how it works in frequency domain, then what we have is this bit pattern formed by two frequency combs, right? So they start to detune. So eventually, there is not so much overlap anymore between the T's, which forms a pretty much confined RF spectrum, right here. If you look at time domain analogy of this process, and what we have is it's like correlation between pulses, right? When pulses perfectly align, we have a strong signal, a lot of power on photodiode, and then they start to drift apart. So we'll have only partial overlap, and correlation function is smaller. So in time domain, what we form is this voltage pulse, right? That we can detect and then do Fourier transform and reconstruct the spectral information of that. So that's how it works. And this is one of the applications which is taken also from this reference in Optical in 2016 of a hydrogen cyanide gas, which is quite toxic. And you can see this beautiful extraction of the absorption feature of this gas and also phase across this feature. So this is pretty much my only questions. So Jean, I hope you're very happy. And I want to discuss just a few metrics for the use of frequency combs, just to give an idea of it's not limitless, so we have to keep in mind certain limitations with regards to the bandwidth of the comb and the general power of the comb and how it ends up playing role in signal-to-noise ratio of our signals. So if we look at this dual comb spectroscopy scheme, then what we have is so the bandwidth of our frequency comb, right? So delta nu here divided by the number of modes, which is m, is becoming an important factor. And there is always a trade-off between the bandwidth and the acquisition time that we need to spend to acquire good quality signals. So the larger the bandwidth, the more the time we need to spend, or alternatively, we can choose a frequency comb with a broader spacing. So that would also work. So if you don't want to increase the acquisition time, if you want to keep it very short, and we want to have a broad bandwidth, then we better choose frequency comb with broader spacing between the lines. Make sense? Very good. However, there is another figure of merit that we have to keep in mind, and that relates to the signal-to-noise ratio. So we have a certain power, right? Average power in our frequency comb source. So if you have a broad band frequency comb source, it means that most likely it's going to have many T's. So the power per tooth, so to say, becomes less and less. So tau and comb is entire power. So if you have many T's, which is this M, large M, then power per tooth becomes really small. And we have to remember that signal-to-noise ratio scales with the power per tooth. So then we end up with this trade-off between how many T's we have in our spectrum and our signal-to-noise ratio. So we either have many T's but very low signal-to-noise, low signal, or we have narrow comb, less T's, and we have very high signal-to-noise ratio. So everything kind of sits on these curves here, and it's up to us to decide what to do about it and what we need for our applications, and for what we are measuring in terms of the strengths or the absorption strengths, right? We might end up being okay measuring at high bandwidths with many T's, or we might need to compact everything into smaller bandwidths, have less number of T's, higher power per tools to get signal-to-noise ratio right. So with this, I would like to just conclude and say that especially dual comb scheme is very powerful because it allows you to avoid those scanning interferometers and do things very, very fast, down to sub-microseconds, which is really, really fast. And that's where we need to get with all the biological imaging. We need to measure things before things change. And biology changes all the time. So this is where, I guess, for the Center of Excellence Comms, we are taking ideas to implement single and dual comb spectroscopy towards biological imaging and microscopy to speed up things without loss of resolution, spectral resolution, and signal. Thank you very much.